So welcome back, everybody, to the second lecture about lattice field theory, a primer of methods and results by Davide Vadacchino. I think that we can start. So without further ado, please, Davide.
Okay, thank you very much, Claudio, and thank you again to the organizers for organizing this set of lectures. Yesterday, we did a survey of the theoretical foundations of the lattice regularization of quantum field theory. The main steps, let me recap briefly. The main steps are to express actions in terms of Euclidean space, where we can then, where all the usual objects are well defined, and then to discretize actions by substituting integrals with sum and derivatives with finite differences. We have seen that for scalar fields, this operation goes through quite easily and in a straightforward manner. Not so for the fermion action that required some more reasoning, because of the fact that symmetries are broken when one discretizes space-time. And then we have seen that, to the contrary, gauge fields are discretized in a very, very direct way by discretizing parallel transporters. Today, let me add just that I mentioned that one of the advantages of this lattice approach is the possibility, once you have discretized your system in Euclidean space-time, you have the possibility of simulating the system on a computer. So the lecture of today dwells on the simulation of Euclidean quantum field theory on a lattice. So what I will do during this lecture is talk mainly about Monte Carlo methods in general. I will do an example for pure gauge fields. So I will give a practical recipe to implement the simulation. And then schematically, I will explain how to face the problem of simulating dynamical fermions. If not complete, at least this schematical explanation will at least try to explain the problems that affect the simulation of dynamical fermions. And then I will present some results for the global spectrum of a theory that is useful in beyond the standard model physics. I will explain the methods, and then I will present the results. Okay, so let me go to the next. Okay, so let's start with Monte Carlo methods. Okay, so as always, there is a problem with my keyboard. No, sorry. Okay. Okay, sorry for this problem. Very well, so introduction. Now, in this introduction, I will try to explain in general what are Monte Carlo methods, what are the logic behind it. So let's start from the generic expectation value of some observable in a system in which we have both fermions and gauge fields. So we have an object that has this shape where we have the Wilson action, SW, and then the action, the Yang-Mills action. Sorry, so this Wilson action is the Wilson fermion action, and this is the Wilson gauge action that I have explained to you the last lecture. So now there are several methods to compute this object. One method that has had historically an important role is the so-called strong coupling method. So in the strong coupling method, one takes advantage of the fact that there is a regime of the phase space, the phase space of the discretized system where this quantity is much smaller than 1. So what emerges from this view is that one can express observables naturally in terms of lines, closed lines and open lines ending on fermions on the lattice. For example, path done like that when one has these, or else for Wilson loops, one can sum over surfaces bordered by closed path. So here I have a square that is going over the surface. So one is able basically to compute things in powers of beta. Now, what is the problem? Obviously, we are the continuum limit happens for infinite beta, and this is an expansion around beta equal to 0. So in principle, we would like to extend this expansion so that it reaches the scaling region in which we have experiments, but it is not possible because this strong coupling expansion has a finite radius of convergence, and in particular, there is a transition called Raffanin transition that prevents us from getting to the continuum limit with the strong coupling method. Let me note that there have been some important results that have been obtained with this method, namely regarding the phi to the 4th theory. And there you have to look for Blücher papers and Münster. And yeah, there are very nice results. Then we have the usual weak coupling. And let me stress that weak coupling looks like perturbation theory, the usual perturbation theory that one learns in school, in university, I would say. Here we have lattice perturbation theory. Now, lattice perturbation theory is a quite complicated framework in which to compute things in the neighborhood of the opposite limit to the one that is obtained in the strong coupling region. And apart from this, if one cannot obtain results with these methods, one must resort to Markov Chain Monte Carlo method. That is often abbreviated with Markov Chain MCMC. So, what is the idea between this method? The idea is that if we are able to collect a set of configurations of the system such that the vacuum expectation value of the observable O for a large set of these configurations is equal to the average over the configurations that are in the set, then we are very happy. Then we can just simulate the system, collect a certain number of configurations, and then compute the observables on the configurations and average. Now, this is possible. This is possible if these configurations are distributed according to the following distribution. Now, this comes from the fact that we have a map between quantum field theory and classical statistical mechanics. So you see this object E of C that stands here in the exponential is related to this. So if we are able to collect sets of configurations whose probability density, probability distribution function is e to the minus EC, then we can just compute observables. Now, this space that I will call, let's say, C, is very high dimensional, because imagine just in the case of gauge theories, you have one matrix for each link of the lattice, or in the case of a scalar field, you have a number for each side. So in general, the possible configurations cover a space that is enormous. So the strategy, instead of trying just to sample statically, that is to extract randomly one configuration and then computing something that has this distribution function, we can just imagine a dynamic process, dynamical Monte Carlo. So we define basically a stochastic process such that we have a sequence of configurations and the stochastic process I will call P, and this P will make my configuration evolve in the sequence, and I require from this configuration that the set of configuration in the sequence is distributed with pi c. Very well. So to be a little bit more definite, let me explain what is a Markov chain. Obviously, I will focus on the concept, so I won't be very rigorous. So for simplicity, consider a discrete state space. Now, a Markov chain is a sequence such that the state Ci plus 1 only depends on Ci. Now, this is often this is described as the future depends on the past only through the present. So this means that basically configurations that are separated by two steps are the configurations are statistically independent. And obviously, our Markov chain, in order to be useful to us, must have pi c as an equilibrium distribution. So not any Markov chain will do. Now, if we define the probability that the process will make us pass from configuration Ci from configuration Cj, and I will call this quantity Pij, then we require from this Markov chain, well, an initial, a very reasonable property is that if I am given a pair of configurations, then there must be a way in the process such that these configurations can be reached from one to another. So if I have two configurations, E and J, there must be a path, at least one, but not necessarily only one, so that I can get from one to another. This is called ergodicity, and it is written as follows. So for each pair of configuration, there must be an n such that if I repeat the update a number n of times, and I write it in this way, then this probability is more than 0. This means that there is a finite probability that from any state I can get to any other state. And this, the name is already informative of this property. And the other property that I require from this Markov chain is that the probability density pi of c is equilibrium distribution. This means that if I let my system run for a certain time, obviously I can start it in a certain configuration that is that might be in a very improbable corner of the distribution function, but then eventually the system, by successive updates, will visit the states of the system with that probability density. Okay, so this means that the probability density will not be changed by the updating process, and this is written as follows. So I have my the probability at step I will be equal to the sum of the probability of so the probability of configuration J will be equal to the sum over initial configurations I that appear with probability pi. So let me stress some properties. First, here we have some sort of stochastic time, because we can define a time, for example, at each step of updating. This time, as the stochastic time, is not necessarily physical. So we define a generic stochastic process. It might bear some resemblance with some physical phenomena, but in general, it is not physical time. Then imagine we have succeeded in building this stochastic process. We want to compute averages with this method, so averages of observables. And we know that because of the central limit theorem, whatever form pi takes, averages will have fluctuations that behave as 1 over square root of n for n that tends to infinity. So this tells you that Monte Carlo method is the last resort. Okay, so if you find a method that works well with a better convergence, use it. Unfortunately, for the regimes, for the physical regimes in which we are interested, this is the only method, and it has shown to be quite effective over the years. Now, there are some considerations that one should do in general about this kind of construction. So again, imagine you have succeeded in building this stochastic process. One could ask questions about the fact that successive configurations are correlated. So the final results will not be, you cannot just ignore the fact that these successive configurations are correlated. And then you have to ask yourselves about the efficiency, because say you are able to construct a Markov chain with the desired equilibrium distribution, it might still be that the process is terribly inefficient, so it will visit the phase space very, very slowly. And this actually happens in real life cases. So let me just briefly state the difficulty with autocorrelations. As I said, usually successive configurations are correlated because they are part of a sequence that is obtained with a process that acts on a configuration to produce the next in the sequence. Now, when we have collected a set CI of configuration, usually we want to estimate some observable O, and to do this, we take the mean and we consider the variance. So let me write it in this way. And the variance that is equal, you all know, to the unbiased estimator that one uses when one uses the estimator of the mean. Actually, these are estimators for the real quantities. And by real, I mean the exact quantities that one would be able to compute if one could analytically solve the system. So these and these. If one is able to compute either of these, then the result is usually stated as follows. An average value plus its error, and this usually is written like that. However, if you have autocorrelations, this is not true. And the reason emerges if one computes the variance of this object. And the variance of this object in the true with the true probability distribution function can be written in this way. And then one can write it with the sum over n. And now I just want to show the first steps of the calculations, and then I will urge you to do this calculation. It is instructive. Okay, so at this point we have closed the mean, the average value, and then look at this expression. We have a sum over I and j of an expectation value of I minus average value of O times OJ minus average value of O. Now, at this point, you see that if there were no correlation, one could say that the average value of the product of OI and OJ is equal to the product of the average values. And as a consequence, we would have that the standard error of the average value is just 1 over square root of the standard error of the sample. If there are autocorrelations, you will have mixed terms. So these terms that are in the average of the products will not vanish anymore. You will have a complicated expression, and I leave you as an exercise to do the calculation. It's only algebraically complicated, but there is nothing fancy from the conceptual point of view. And in the end, by the way, you find it in the lecture on Monte Carlo methods by Alain Sokal. And the final result is that this variance of the estimator of the mean will have this expression. And this is the first encounter with this quantity, that is the integrated correlation time. Autocorrelation time, sorry. And this is a very important quantity because effectively it tells you after how many steps the two configurations that you are considering are effectively decorrelated. So they are completely independent. The expression of this autocorrelation time is complicated if you haven't done the calculation. But I'd like to report it here because it bears some resemblance. I mean, its shape is quite intuitive actually, so it's better to report it. So what this object measures is the correlation between the fluctuations with respect to the average value of O. So fluctuations will be correlated and will give rise to this autocorrelation. And note something that each observable may have its own autocorrelation. So, for example, if you compute the internal energy, that is, in the case of gauge theory, is the plaquette, this is the first observable that you check when you do a program of simulation of pure gauge theories, and you find that its autocorrelation is quite small. So you update the system and you see that the starting value of the system, let's say with all the links with a certain value of the dynamical observable. So in the case of, for example, an SU3 gauge theory, I can start all my links in the system with value 1 unit, the unit matrix. And then I update the system, and depending on the value of the Baire parameter, the value of the plaquette, of the action, basically, will accommodate on a mean value. Now, how long this takes is called the thermalization time, and it is related to the correlation capacity of my stochastic process. So if I take two configurations that are separated by more than the integrated autocorrelation time, I can be confident that they are independent. Now, this also tells me another thing, that the effective number of configurations that I have in my sequence is not n, but rather it is n divided by twice the integrated autocorrelation time. And this, I understand it from this formula. I recover the usual formula for the scaling with n of the error by substituting n with nf. Very well. So once I have this integrated autocorrelation time will help me understand how efficient my algorithm is. Because, for example, if I build up an algorithm that has the correct equilibrium distribution, but a very large autocorrelation time, I will not produce independent configuration, and it will be very difficult to compute observable without a statistical bias. So, just for definition, let me tell you about a general framework that has been worked out by Metropolis and Hastings, but that is applied in basically all the algorithms that are around. Let me just state a very important property, that of detailed balance. So I've told you that one of the two requirements that I ask from Markov chains that are interesting for the use that we want to make of them is that they have pi c as an equilibrium distribution. Now, showing that a certain stochastic process has a specific equilibrium distribution is quite complicated, especially when the space of state is not discrete but continuous, like the case in which we are interested. But we can require something less, that is a sufficient condition. And the rationale is to imagine that we have our stochastic system that our stochastic process that visits our space of configurations, and we require that if we require from it that it leaves unchanged the distribution of states, and this happens if in the space of configurations there are no sinks nor sources of probability. That means that in every point the situation is stationary. And this is expressed with the following condition. So the probability that we exit from configuration L must be equal to the probability that we enter in configuration L. If this happens, we are at equilibrium. Now, this I will call property 1. Metropolis and Hastings is a general framework to work out a shape for these probabilities PLM. And the logic is to split the definition of P in two parts. One part in which we propose a new configuration. New config. And one part in which we accept or reject it. Formally, say you want to write down the probability Paj of going from configuration I to configuration J. This means splitting P into Pij not. And this means propose the probability of proposing J. And then Aij, that is the probability of accepting the change. And this for I different from J. For I, for the probability that the system doesn't change amounts to the sum between the probability that the proposed configuration is the same as the one in which we are, so that we propose no change, and the probability that is a sum over J that the proposal that we made in the first step has been refused. So the complementary to the probability of accepting it. So, and this means change not accepted. As you see, I have completely determined, at least formally, the matrix Pij that allows me to evolve the system. Now, obviously, this is very, very abstract. Now, if I take this that I call 2 and I plug it into 1, I obtain a relationship between P0 and P0 pi j and Aij pi j and the P0s. And this you can do the calculation. It's very simple. So what this means is that given a certain pi j, a certain probability density over configuration space, the Aij and the Bij must satisfy this equation. Obviously, for each Ij. Now, in general, I can define Aij as a function of this ratio. And I can define this ratio as the variable z. And then I see that this equation is equivalent to asking that f of z is equal to z times f of 1 over z. If I am able to solve this functional equation, then I have a solution for my Aij. Now it turns out that the solution is not unique. And for example, I have that Fz is equal to the minimal value between 1 and Z itself, but also Z over 1 plus Z. So the solution is not unique. And this corresponds to different implementation of the Metropolis-Hastings algorithm. And this material, you find it in SOCAL, in lectures from SOCAL that are mathematically oriented, but very readable and precise. Now, let's say I want to apply this algorithm to the case of the Wilson gauge action. So let's say I want to simulate pure gauge theories. So for a pure gauge theory, we know that the generating function is the following. Where the Wilson action is a function of the links on the lattice, and it is equal to beta times the sum over the plaquette. I will write it in this symbolical manner with the sum with the subscript PL, and then I have 1 minus 1 over 2n real part of the trace of U PL. But again, this is the plaquette. I write it in this symbolical manner because I don't want to bother with the indices and sides. Now, in this case, what are the variables that determine the point in configuration space in which I am? Obviously, the set of links for all the links on the lattice. So since each link is an element of the gauge group, my space C of configurations will be the direct product over the links of the lattice of the gauge group. And so I repeat what I said in the last lecture. This is a well-defined integral. If the group is compact, we can define a Haar measure that is unique. That is the only invariant measure, and everything is mathematically well-defined. And we don't even have to fix a gauge because every orbit is taken into account perfectly. Now, this action has a very interesting property of being local. So say that I only propose a change in one specific link that I call L, then the change in the action will be a function of only UL. Now, in the previous slide, I have shown that this object Aij was equal to a function of the ratio between Pi and Pj and the ratio between P naught Ji, Pij naught. Now imagine that in my stochastic process, I have a process that proposes the configurations equally in one direction and in its inverse. Then this is a function of Pi, Pj, but this is simply the difference between the actions of the system in the new configurations and in the old. And I have said that a solution to the requirement of detailed balance in the Metropolis-Hastings framework is just this. So basically, I can propose to change a single link, and then the proposition is accepted with the probability that is written here. So what I do in practice is that my proposal will be a small variations of the matrix for a reason that I will now explain. So I choose basically epsilon A small and random, and TA are elements of the algebra of the gauge group. Basically what happens is that this is close to 1 and it belongs to the group, so that the element, the value of the link variable is slightly changed. So the action changes slightly, and we have a good probability that the change is accepted, because it will tend to be less than 1, but still not very small. Note that there is a quantity that is very important. The ratio between the ratio between the number of accepted proposals and the number of proposals itself. This is called acceptance ratio, and this is another way to measure the efficiency of the algorithm that you are using. Say you take, for example, in this case, a very small epsilon, then the acceptance ratio that I will call RA is large, because the change in the action is small, so the change is basically always accepted. However, the system, the configuration space of the system will be visited very slowly, because if epsilon is very small, then the matrix defined on the link will change of a very small quantity. To the opposite, if we have a large, let's say, here, let me be definite, okay. If we have a value of epsilon that is smaller than 1 but still large, the acceptance ratio will be small. So I will propose large changes in the configuration, but because of the way the Metropolis Hastings algorithm is defined, the new configurations will usually be refused. When they are accepted, they change a lot, the configuration of the system, but they are usually refused. So this is an example of what you can do with the Metropolis Hastings algorithm. Now, let me just state, in real life calculations, one uses a variation on this algorithm. The variation is called heat bath, and one can use it for pure gauge very effectively, and it is different from this Metropolis Hastings technique in that we choose to propose the configurations, so we choose Pij such that they are always accepted. And this we can do because the action is local, so exactly as in simple models of statistical mechanics, we are able to take into account the effect of the neighborhood of the local dynamical variable to invert its probability distribution and extract random numbers with the right probability distribution. And these you find in very well explained in the lectures on lattice field theory by Kari Rummukainen of Helsinki University. Very well. So now let me just schematically explain what happens if we try to simulate fermion fields. Now, we have seen that the action has the following shape: a to the fourth sum over sides of psi bar n d n m psi m. Now remember that these two objects are Grassmann variables. So there is this famous property called Berzin integral that tells you that if you do this integral, you will find the determinant of D. And I think I made a typo in the last lectures. I put a square root. Anyways, let's say you have a theory as before of fermions and gauge fields. Then your observable will generically depend on all these. It will be a function of the fields, and the expectation values will be computed in the usual way. This time I have to plug in the observable O that depends on psi, psi bar, and U, and then I have my statistical weight. So the fermion action will also depend on U, because it is the action of a fermion in a gauge field, and it will depend on psi and psi bar, and then we will have the Wilson action. Now, an example, usually this observable is some correlation function. So, for example, in the case of an n-points function, this will be equal to. Now, here something interesting happens. This object will be a string of propagators, and from the representation, from the following representation of the fermion action, in the continuum, that is also valid on the lattice, we see that the result of this calculation, when one integrates the fermion fields by performing the usual functional derivatives, one obtains a string of correlators, then a determinant, and then the gauge field. So this amounts to the calculation of inverse matrices of the fermion determinant times the determinant in Young-Mills. Now, this, note that the matrix D is itself enormous, but it is sparse because it connects it connects nearest neighbors. So it is a very large matrix because we have very many links and sides on the lattice. Remember that it is a 4-dimensional lattice. Also remember that this is a direct product with gauge degrees of freedom as well. So it will be really large. So it will be expensive to compute both the determinant and also the inverse of D. Now, an idea could be to use the determinant of D as a statistical weight, were it not for this problem of the fact that it is enormous. But then the determinant of D is incredibly noisy. So you, additionally to the fact that it is expensive to be computed, it is also noisy. So usually one does not use this determinant of D as a statistical weight, except in cases in which it is very easily computable, for example, in a small number of dimensions. Then note also another property of this determinant. Don't know if you remember, but we had signaled this property of the Dirac operator on the lattice, and this, as a consequence, has that the determinant of D dagger is just the determinant of gamma 5 D gamma 5. And since gamma 5 has squared 1 and the determinant, you can just move around the matrices, then this is equal to the determinant of D. And this means that D is real, but it is not necessarily positive. So this might mean that my program of using the determinant as a statistical weight might fail. And indeed, it does in certain cases. So a possible solution for that is to use approximations in the computation of the determinant to write it as a function of positive quantities. But there is also the possibility of choosing to work in a system where this problem doesn't show up. So for example, in a system with two flavors of degenerate fermion, we have the functional integral as follows. Then we have a sum over the actions of the two fields, the two fermion fields, with the same operator. And then we have the Wilson action for the gauge part. Now this means I can integrate the Grassmann fields, and the result will be the square of the determinant. So in this case, I have this positive quantity that I can use as statistical weight. Very well. Now, let me just schematically explain how one is able to update these configurations of fermions. Now, as I told you, if you wanted to apply the Metropolis Hastings algorithm, you would have to produce configurations of U weighted with the determinant of D that depends on U, and then the Wilson action. Now, this quantity will be, as I said, very fluctuating. So, and by the way, it is also non-local. So you will need to update the whole lattice before you can even propose a new configuration. And this will have an acceptance rate that is incredibly small. So this is not the best way to go about the problem. Notice, however, that I can write the determinant of D times D dagger as a functional integral over boson fields. That are complex in this manner by using the fact that I put a power -1 in the exponential. And if you remember the rules about Gaussian integration of scalar fields, you realize that this is the correct formula for a Gaussian field. So I have a way to represent the determinant as a function of something that I know how to interpret. Then I write, for example, an observable O that if I have a functional integral over which I want to compute this observable O, I would have something like that. And this is the generic case. So let's say that I add artificially some new degrees of freedom P. With Gaussian weight. Then what I can do what I can do is that I can represent this whole action in this way. Sorry, in this way. And then what I do is I integrate numerically. I integrate numerically in P and Q, in this case, P and U, with the Hamiltonian given by 1/2 P squared plus S U. As a result, I will obtain a new configuration that will have conserved the energy, because I have done not trivial, but a simple integration in phase space according to a Hamiltonian that doesn't depend explicitly on simulation time. And then I can propose to Metropolis Hastings, and this will have a certain acceptance rate. This is the way most of the simulations are carried out. Very well. So two very fast observations about Monte Carlo simulations. Now, let me just state that dynamical fermions, I hope that I have been not, I have not been very hermetic in my schematical explanations, but I hope I conveyed the fact that they are very expensive. So one and very hard to program, by the way, for the amount of small parts, small separate parts that one should implement. So usually what one does is to neglect the effect of quarks in the sea and works in the quenched approximation. How do you do that? You send the mass of quarks to infinity. Then it is impossible to extract a quark from the sea, and you are left with the dynamics of the gauge field. Keep in mind that in this case, you still have valence quarks that, however, are static. For example, you may want to measure the static potential, and then you can do that. You place two static quarks and you simulate the dynamics of the gauge field. A third property is that usually, especially in the pure case, we update the field locally. And this means that if you have something that depends non-locally on the configuration, for example, the topological charge, I make an example, you have a critical slowing down when you get close to the continuum. This actually, topological freezing is probably slightly different. It's not the right example. But what happens is that your integrated correlation time will behave as the minimal between the size of the system will grow as we flow to the continuum limit. It will grow with the minimal quantity between the correlation length and the size of the system in lattice unit to a power that is called the dynamical critical exponent. So what happens is that the more you get close to the continuum limit, the more the system will take time to effectively update. So a related example, as I said before, is that of topological freezing, but that is quite different actually, because in that case, say you have a gauge theory and you have your theta vacua, sorry. Now your updating is local, so your system will not be able to overcome the potential barrier that separates the different vacua, let alone that on the lattice, this vacua will tend to be separated by an infinite well in the continuum limit. Very well. So, okay, so I think that it is time for a break, a 5-minute break. What do you say, Claudio?
Yes, we can make a 5-minute break, and if there are questions, please feel free to ask.
Okay.
Okay, I think that there are no questions, so we can have a 5-minute break and we resume at 10 past 12. Okay.
Okay.
Okay, Davide, you can share the screen.
Yes, sorry, I was having trouble. Okay. Okay, can you see?
Yes.
Very well. Very well. So let's go on. Now, what I wanted to do at this point, having done an incomplete and schematical survey of the methods used in Monte Carlo simulations, I wanted to illustrate a few results on the problem of confinement, on the problem of strings, but actually very, very superficially, and on the global spectrum. During this part of the lecture, I will mix general arguments with their application to the specific problem of computing the global spectrum. And obviously, I will define, I will say what globals are in due time. But let me start with the problem of confinement. So as you all know, you cannot observe a free quark in asymptotic state, despite the fact that there are many experimental facts that point to the fact that quarks exist, among others, the multiplicity of hadron states, jets, etc., etc. However, the problem is that despite the fact that this phenomenon has been known for many, many years, it has no explanation from first principles yet. There are models in which you are able to basically demonstrate it. There are many phenomenological models to try to explain the phenomenon in the most realistic systems. So let me just cite the U1 theory in 2+1 dimensions. There you can explicitly demonstrate that two static charges attract each other with a linear potential. You can compute an expression for the string tension depending on the bare parameters of the system, and basically you have solved the problem. In other cases, you have models, for example, the dual superconductor model, in which an analogy with what happens in a type 2 superconductor, in which the Meissner effect expels the magnetic field, so that the magnetic field, instead of being spread over sorry, let me write a monopole here and another monopole here. So the magnetic field, instead of being spread over space because of Meissner effect, will be squeezed into a tube. Now, this is something that is related to what happens in particle physics. And all this happens as strong coupling. So the lattice is a perfect tool to study this regime. And in particular, on the lattice, you can easily study the static potential between between a quark and an anti-quark. You can study the global spectrum easily in the quenched case. well, easily. You can do it. And then you can work out other quantities. For example, the universal quantities, like the ratio between the mass of the tensor state of the system over the mass of the 0++ state of the system. Let me spend 2 words on that. If you have a system and you are able to define an energy momentum tensor, you are able to work out the correlator between it. You are able to decompose it in representation of the Poincare group, and you can work out the correlator between the different parts of the energy momentum tensor. So you are able to compute the correlator between its trace part and its antisymmetric part. And it turns out that each of these has a different mass. And this only depends on the possibility of defining an energy momentum tensor and on the dimension of the system, basically. So you can put forward the hypothesis that this ratio is universal, and indeed this happens, and this is shown quite precisely for the spectrum of globules. Now, why is this important? This is important because we don't know the mechanism that underlies confinement. Every additional clue that we can get from lattice data that tells us something universal about the spectrum is an important step forward in unraveling this problem of confinement. Now, in the case of SUN theories, you have a lot of material on globules and string. So let me say lattice gauge theory. And the author that you have to look for are the following: Mike Tepper, Biagio Lucini, Andreas Atinodorou, and others. And also for SP2N groups, I work on that, and others. And you can look on Inspire and find the study of the global spectrum for SP2N gauge theories. Very well. So now let me state some more properties of this confinement problem from experiments, namely from the fact that we have mesons lying on red trajectories, and also from the spectrum of quarkonia. We know that we expect that at large distances, this static potential I was talking about before will behave linearly. Okay. Now the important quantity here is the string tension. The string tension will be, in the absence of dynamical fermions, the only scale that we have in the system. Sorry, the lowest scale that we have in the system usually. And its value, how its value depends on the number of colors, on the dimension, and how it scales, might give, again, important clues about the confinement mechanism. Now, as you see here, we have a behavior for large distance between the static charges. Actually, there is a framework called effective string theory, in which we are able to compute the corrections to this potential at finite R. Now, effective string theory is based on the observation that the formation of the string in a system breaks a few of its Poincare symmetries, namely the transverse translational symmetries. As a result, you have a certain number of Goldstone bosons that appear, and these physically are the fluctuations on the worldsheet of the string, except that now the situation is different with respect to usual effective field theories, in which for each broken symmetry you have a Goldstone bosons, because here the generators that are broken are not independent. So as a result, you can constrain heavily the effective action in terms of a power expansion of 1 over sigma r and L when the Wilson loop that you are considering is square, or L or T where the time extent of the system is T. Okay. Very well. So there is a nice review that you can look for by Aroni on the theory of effective strings, and there you have also other approaches to different approaches, several approaches to writing down the effective action. Now, there are no clear experimental signatures yet because of a difficulty that I will explain shortly, but we expect that the spectrum of gauge theories contains a rich part formed by pure glue state. This pure glue state that in a certain regime might be described as bound state of gluons are called glue balls. Now, these are very hard to detect because in the real world they mix. They have the same quantum numbers as some of the Q bar states, and so they mix. And in colliders, the signal of their presence is very, very, very hard to see. There are some clues again, because there seem to be some supernumerary state with respect to the patterns that are predicted from the quark model, but it is very hard to tell because there are resonances that have a very large width, so they're hard to separate, and moreover, from the simulational point of view of Monte Carlo simulation, the difficulty in simulating these systems with fermion is magnified by the fact that these glue ball operators are very noisy. So if you add the noise of fermions, you get to the fact that computing the mass of glue balls in the presence of fermions is currently beyond what has been done. But obviously there are people working on it. So these difficulties and the description of the experimental status of glue balls, you can find it in the particle data group booklet. Very well. So why did I say this? Because we are going to describe a system in the quenched approximation. Now, in the quenched approximation, let me, for example, draw the static potential. In the quenched approximation, you have, well, if you expect to reproduce the linear behavior at large distance, you have a potential that is done like that. Now, let's say that you want dynamical fermions. Then you immediately realize that if you have dynamical fermions, at some distance, dynamical fermions will begin to pop out of the vacuum, because if you pull the flux tube that connects the static pair, at some point the energy contained in the flux tube will be enough to create a quark-antiquark pair. And then here, in reality, you have finite error corrections that are done in this way. And this you can compute with effective string theory. So in the end, working in the quenched approximation, you will expect something like that. From here, you get a first approximation on sigma, on the string tension. From here, you get finite error corrections. from effective string theory. Okay, so on the lattice, what we will do is what we will see how to do will be to compute the global spectrum. This will be useful for scale setting. Because sigma is a quantity that we know how to compute experimentally, namely from the slope of the Regge trajectories. So we can use it to set the scale on the lattice. There are more effective methods have been developed. Always remember that the precision of your results is heavily influenced by the choice of the precision of the scale that you use. So using a scale that is not precise won't look good in the final results. So on the lattice, what we will do is to compute the global spectrum. And the advantage is that in the quenched approximations, we have no mixing. So the globals will be standalone states of pure glue. We can neglect string breaking, as I just said. And we will have less noise. Now, in general, how do we compute a mass on the lattice? Now, let me try to face the question generally. So let's say that you have some state in which you are interested, a state that I will call psi, that is produced by acting on an operator on the vacuum. Now, the quantum numbers of psi will be the same quantum numbers as the vacuum, because the vacuum, usually it will have different, psi will have different quantum numbers from the vacuum, but there are also cases in which these quantum numbers are the same. For example, the 0++ global. What I wanted to say is that you choose the quantum numbers by choosing the operator O. For example, if you want to propagate a meson state, you will take an operator like that with definite flavor indices. If you want to propagate a global, as we will see in the next few slides, you take a Wilson loop. Example, this. These are defined, these operators defined on this path produce globals. That is, states of the Hilbert space of the pure glue theory. Now, to compute the mass, as always, we compute the correlation function. So we generate the global or any other state at time 0, and then we annihilate it at time t. Now, it is a very common manipulation to extract the spectral density of this correlator, and I will just write it here for completeness. The manipulations are very standard. So now you see that if you call this quantity Cn, this will be the overlap between what? It will be the overlap between whatever is created from the vacuum by operator O and the state n in the energy spectrum. So it is a very important quantity, as we will see. Let me just state that the behavior for large Euclidean time is dictated by the first overlap, so the overlap on the ground state of the system, times exponential of minus E naught t, and with corrections that behave as follows. I have simply factored the term containing E0. So you see, and then larger corrections. Let me define this object like this. So from this expression that I want to stress is very important. We see several things. Well, first of all, that the noise is constant. Usually in a simulation, you have a constant noise when you compute this correlator, but the signals, it goes to 0 with an exponential of minus E0t. So if you consider the ratio between the magnitude of the signal and the magnitude of the noise, this will go at least as e to the E0t. This is a very well-known problem of every correlator in lattice gauge theories, and usually the solution is to maximize the overlaps, because there is no other way to solve this problem. Okay, and you also have another problem here. Imagine you have computed this correlator over a certain range of t. If the t is not large enough, you will have contaminations from excited states. So in this case, I have written E1. This will be obviously reduced with the ratio of C1 to C0. Now, in practice, what happens is that we try to isolate the contribution of the single exponential by computing this effective mass as follows. It is defined as minus 1 over a times the logarithm between c plus a and c of t. So now it is clear that this will extract at very large t. It will just be equal to E0. But in practice, what happens is the following: you have your t, you have on the vertical axis, you have your effective mass, and the contamination at small t will result in a behavior like that. So at some point you will have a plateau. Here you have the single exponential. So the contamination has faded out. So basically you can, from here on, you can fit with a single exponential. Let me write it correctly. Here you have, in this area, you have the contamination from excited states. So usually this is what you do. Now, it is not guaranteed that by choosing a certain operator, you are able to actually find this plateau called mass plateau. Okay, so it is not guaranteed that you are able in the end to fit with a single exponential. A way that is completely general to define the operator that maximizes the overlap between the state that you create and the states in the eigenvalues of the Hamiltonian in which you are interested is the variational method. So this starts with a definition. So I define the variational mass as follows. I have 1 over A logarithm. And now imagine having a single exponential, the behavior of CT with a single exponential, and the corrections. As I have shown, the addition of corrections will increase the effective mass. I have shown it in this plot. Now, what I expect is that if I have a single exponential, I will have a plateau, and any contribution from contaminations will overestimate the effective mass. So here I just choose the minimal value, sorry, the maximal value for this object here. That is written in a quite abstract way, but it is understood that this is the system that shifts, this is the operator that shifts my configuration from one time slice of the lattice to the next. And so this is a form to write let's say the exponential decay of a correlator along one step in time. So this will give me e to the minus e naught ideally, and if I maximize this e to the minus I naught, it means that I have minimized e naught. So I am trying to find the mass plateau of the system. Now generically, to find this optimal state, psi that realizes this condition, one should define a generic linear combination between what? Between all the operators that act in a certain with certain quantum numbers. And then the fact of finding the best state among the optimal state means finding the optimal linear combination. Now, if you take the correlation function between the states created by operator I and operator J, I will write it in this way, and you perform a spectral decomposition, you see that you will have objects like that. Okay, now this is a matrix. It is a matrix in I and J. And it has the property of being real, and it is also symmetric. Now, it is real because when we choose our operators, we usually want to choose eigenstates of charge conjugation and parity. So if we choose eigenstates of charge conjugation and parity, this amounts, at least for gluons, to choosing the real and imaginary part of an operator, and the real and imaginary part are real quantities. And so as a result, this matrix is a real matrix. Because it is symmetric, it can be diagonalized as follows. Now, these V's would be the eigenvectors of this matrix C, and they represent physically, basically, they can be ordered in, look, we have many eigenvectors and eigenvalues. Let me write it in this way. And what you can do is that you can order them so that the lowest is the largest. And in this way, what you have done is to effectively solve this variational problem. Because now, now basically you know what is the shape of lambda n, and the shape of lambda n you can find basically by noting first that by a collateral reasoning, by noting that if you try to invert this to solve this problem at large T, it is very probable that you will have problems of instability in the inversion of the matrix that is necessary to diagonalization. So instead, you solve what is called a generalized eigenvalue problem that is different in this way. You just pick the eigenvalues between 2 time slices instead of taking all the way to the extremes, and it turns out that this solving this problem amounts to setting the determinant of this object to 0. But we know that in the canonical basis, this object is just a diagonal matrix with eigenvalues done like that. And this is from the spectral decomposition. And so in the end, we have that lambda n is equal to the exponential of minus en t minus t naught. If you choose t naught equal 1 and t equal 0, sorry, t naught equal 0 and t equal 1, you can diagonalize the system. You can also do it at later times, there is no problem, but usually small t is where the signal is stronger. When you have done that, you find yourself with a diagonal matrix with a sequence of elements along the diagonal. If you order them using the magnitude, then you can fit each to the correlator. And let me now explain this obscure writing. Well, I have used LT as the time extent of the system. A is the lattice spacing. And why did I use the hyperbolic cosine? I used the hyperbolic cosine because on the lattice we have periodic, usually we have periodic boundary condition. So if I represent the lattice like that, and its replica, periodic replica like that, if I correlate these 2 points, I will also have the contribution of this point. And so I have a sum of exponentials, and as you know, a sum of real exponentials can be written as a hyperbolic cosine. Okay, so another important information that one can gain from the study of these correlators, and especially of this variational method, is about, probably, let me erase this and report it here. Okay, let me. Okay, is the information that is contained in the eigenvectors. These eigenvectors contain the linear combination that is the optimal linear combination that will solve our variational problem. So they can be interpreted physically as form factors. Being the linear combination that best solve my variational problem, they are also those that have the best overlap with the state that is propagating. If they have the best overlap with the state that they are propagating, it means that from the point of view of quantum mechanics, it is describing the propagating state best than another state that has a smaller overlap. So we can see these this quantity psi as form factors of globules, and it would be an interesting study, for example, to see how this changes in different conditions. And but we will have a little more to say about this in short. Now let's consider the case of applying this variational method to the pure glue spectrum. Now, this pure glue spectrum is generated by operators that are Wilson loops, defined on path gamma. And now on the lattice, I can define two kinds of paths, the contractible ones. For example, a closed path, sorry. Let me draw the fact that we have periodic boundary condition allows me to draw on a torus, but I will just draw on a cylinder. So in the case of a contractible path, your path is done like that. And you, as the name says, you can contract it. But you can also have this other path that is non-contractible. So we have our cylinder. We start from a point, let's say this point, and we go over the cylinder and we come back. Okay? This will be a non-contractible path. Now the difference between them is that these live live in non, sorry, I am unable to speak and write at the same time. These contractible and non-contractible operators, so the properties of path, I have transferred it to operators, lie in different representations of the center of the gauge group. And this is also related to a property on which I don't have time to dwell too much, but the fact that in pure gauge theory, you can observe a deconfining transition corresponding to the breaking of the center of the group. And this is related to the fact that if I do a transformation in which I transform the time-like links as follows with an element of the group, you immediately see on a time slice, for example, you can do it on just a time slice, and then you realize that for every closed path on the lattice, you have an invariance with respect to this transformation. Instead, if each link is traversed only in a sense and not in the other, if each time slice is gone over only in a sense and not coming back, then this Z factor will remain. So basically, you have some observables that are invariant under the center, some that are not. The action is invariant, so you expect an invariant vacuum. Now, what happens is that under in some conditions, this symmetry is spontaneously broken. And so this signals the confinement on the lattice. Very well, so this tells us another thing. These states are called globules, just to be definite, and these states are called torelons. Now, the fact that they live in a different representation of the center of the gauge group tells me that they do not mix. So I can study the spectrum of globules separately from the spectrum of torelons. Now, let me do a survey of the properties of the spectrum. In continuum quantum field theory, I would use Poincare invariance to label my states, and I would find that I am indeed able to normalize them and to perform all the manipulations that are needed, for example, to extract a Cullen-Lemma representation. I can completely represent Poincare group in my Hilbert space. On the lattice, instead, I have broken Poincare symmetry because I have discretized space-time. So I have broken translational invariance down to a discrete subgroup. I have broken rotational invariance down to a discrete subgroup. Keep in mind that we are in Euclidean space, so we are always speaking about rotations. And we are left with the group of symmetries of this object, this cube. That is the elementary cell of our lattice. And the representations of this object, the group of transformations in which the symmetries of this object live, you can find it in the famous book on quantum mechanics by Landau and Lipschitz. Honestly, in the French version, you will find it. In the English version, it seems that it is not there, but now I don't know how to solve this. But you can also find it in Hammermesh, for example, the book on group theory. And it is quite funny to construct this symmetry group. So we have discrete translations. So our states will have momenta that are that must lie in the first Brillouin zone, and we work in a finite system. So the momenta are quantized. And we have the symmetry group of the cube, the octaedral group. This group is denoted by OH, and I won't work out how to find the reducible representations, but as I said, the method, the calculation can be found both in Landau and Hammermesh. And it turns out that this group has 5 irreducible representations that are denoted in this curious way. Now, you can imagine that being that I am dealing with finite discrete rotations, so in particular rotations of an angle that is pi halves or pi or minus pi halves, I expect this representation to become I expect the representations of rotations to be decomposable in these representations of the octaedral group. And this will happen in the following form. In the continuum, I expect that the A1 representation will contain the multiple of 4 representations. Keep in mind that you won't find more than j equal 4 on the lattice because of the way the lattice is defined. So the A1 will contain traces of the continuum 0 and 4 angular momentum. The A2 will contain trace of the 3 angular momentum. The E representation will contain angular momentum 2. The T1 angular momentums 1, 3, and 4. And the T2 angular momentums 2, 3, and 4. Okay. So if you add now parity, spatial parity, sorry, not spatial, parity, and C and charge conjugation, you get to 20 so-called channels. So for each representation of the octaedral group, you have 2 new quantum numbers related to parity and charge conjugation. Now, how to build, and obviously, yeah, let me say a word on torrelons. For torrelons, you just focus on the ground state. with the quantum numbers of the vacuum, basically. And by studying the correlator, you are able to work out the mass of the torrents that should be proportional to the length of the operator, and then you can find sigma, and in particular, you use it to set the scale. Now, let me just say a word on how you construct these global operators. As I said, you have a path gamma defined at a certain point in Euclidean space-time, and this is your global operator. Now, as I said, you have quantized momenta, and so you can also define an operator that has definite momentum in this way. And this you can do because the system is translationally invariant, and the fact that you have quantized momenta just means that, sorry, that you have you just can define operators with a definite values of the momentum. What you can do that is very useful is to define zero momentum operators, and you see that if you set P to 0 in that formula, you get the following operators. So what you do is you simply sum over this operator on a time slice, and then you have to understand what happens under the octahedral group. Sorry for the notation, this OH is the octahedral group, this O gamma is the operator. I'm sorry, but I ran out of letters. Now, to understand how this octahedral group acts on the operator, you just apply this, the usual formula, and you realize that this will transform in this way. That is, acting on the operator, I just get a new operator defined on the transformed path. So let me do an example. Let's say that I have this Cartesian axis. I define the closed plaquette like that. So let's say that I act with a rotation by pi halves by an angle of pi over 2 around the z-axis. The result will be an operator defined on the plaquette that has been rotated. And the sense is the following. Okay, so in this way, I am able to use the projector methods that, again, you find in Hammermesh. And with this projector method, you are able to construct irreducible, the orthonormal basis for irreducible representations of the octahedral group. An example is that to measure the channel O++, you will define an operator that is the linear combination done like I am drawing of the plaquette operator. For the state that in the continuum goes to 2++, this will take a slightly different shape. Sorry, not a different shape, a different linear combination of the same shape. Plus the conjugate plus P and C. And this to have eigenstate. So in the end, if you code this and you compute the correlation function, you will be able to get the masses. Actually, this is not so simple because you have UV fluctuations, because these operators are defined at the scale of the lattice, so they will be affected by fluctuations on the scale of the lattice. So you will need to operate with smearing operations, smearing and blocking operations that are smoothing operation and that allow you to magnify the effect of fluctuations on the scales that you like. Now let me, since the time has come to an end, I will just go on and present swiftly the results on the SP2N global spectrum. So the SP2N groups are important basically for two reasons. For composite X models, in which SP2N theories have shown to be a viable possibility to build potentially UV complete models of a composite X, and this is very attractive as a possibility. And then they are useful in the study of large N behavior of Yang-Mills theories as an alternative to the SUN and SON gauge groups. Now, what happens to the global spectrum in general, not only in the case of the SP2N group, is that you measure it in this, you measure this quantity on the lattice. I have told you before that you can measure sigma from the propagation of Torelons, and then you assume that at small a you have this behavior, where this C1 is just a constant, and this comes from the fact that the first corrections to the lattice actions are at power 2. So you expect all the observables to have the first correction at power 2. So from this, you see that the continuum limit that you are after is this one, this term, the first term. And this is the discretization error. What you do is usually to measure the ratio at different values of the lattice spacing, and then you extrapolate to the continuum limit. The same can be done for the large N limit. Where you have another constant. Let me stress that these constants can depend on the representation of the octahedral group. But this time you have a correction 1 over n that is different from the 1 over n squared of SUN. This you can find in a paper by Lovelace on the universality of the large N limit. And in this case, you will represent the data as a function of 1 over n, and usually what you expect is that you have something like that. And this is the large N limit that you are after, and this is the continuum limit. Okay, so what you do on the lattice is you perform simulations at varying values of the parameters so that you get these points. Then you extrapolate to the continuum limit with this functional form, and then when you are computed the continuum limit for several n's, you just try to fit the result. And here you have m over sigma square root, m over sigma square root. Very well, now this is exactly what we have done, and you see in these graphs. Now each graphs represent the channels. Each color represents a symmetry channel, as you see. On the horizontal axis, we have sigma a squared. On the vertical axis, we have the mass in units of the square root of the string tension. Something that you should immediately notice is something that we expect. Representations of the octahedral group that have the same content in terms of representation of continuous rotation group should become degenerate as in the continuum limit. And this is a non-trivial proof of the reestablishment of rotational invariance. And indeed, this happens, as you see from these points. This is the case of SP6, but it has also been done for the other values of n. And for each channel, you can get your continuum limit here and here. Now, if you want to extrapolate to infinite n, you will have to repeat the same fits, but with 1 over 2n, the number of colors. and you will obtain the large n limit as extrapolations, linear extrapolations. So in the end, what you will get is the following spectrum. Here I have represented the SU infinity points obtained by extrapolation in SUN theories in black, the extrapolation in SPN in red à pois, let's say. And then you have all the values for the different values of n. And this is the result of a paper that was published last year. Okay, so I think I have finished. If there is some question, I will be happy to answer.
Okay, thank you, Davide, for the very interesting lecture. So if there are questions, please just unmute yourself and ask. Actually, I have a very small question, just a curiosity, actually. So in your previous slide, I saw that you fit the large n behavior of the global masses as a function of 1 over n or 1 over 2n.
Yes.
Which is the effective number of colors. But in SUN gauge theories, we know that the actual expansion variable is 1 over n squared. Because true. Without matter fields, you cannot have odd powers of 1 over n. So
yes, so the difference comes from the analysis of the diagrams that will contribute to these objects. Okay, so in the case of SUN, in the case of SPN, there is a cancellation between two diagrams because of the properties of SP2N groups, and the leading behavior is not 1 over n squared, but 1 over n. And the same happens for SON. So you can find it. There is this paper by Lovelace, and the calculation is done. It's 2 pages. And so you find that the leading correction is at 1 over 2n. Obviously, we tried to fit with 1 over n squared, and the result was wrong, but very instructive, because the extrapolation to large n, say you have these points here, the curve, sorry, Robbie, the curve did something like that, and the extrapolation was completely off with respect to the points at the largest n. So something that you wouldn't expect happened, so that the correction was large the more you got close to the large n limit. So
I see.
And the chi-squares were enormous. So in the end, we adopted the prescription by Lovelace to keep 1 over n corrections.
Okay.